Hello everyone, my name is Arjun Krishnakumar and welcome to this brief presentation of our workshop paper titled LoRA-DARTS, LoRa Adaptation for Differentiable Architecture Search. This is a joint work with Abhash, Kumar, Shakiba, Moradian, Martin, Rapp and Frank. Let's begin with a brief review of DARTS or Differentiable Architecture Search. DARTS is a gradient-based one-shot NAS approach. The method trains a supernet. The supernet subsumes all of the architectures in the search space. The architecture that is searched for and its weights are jointly optimized. DARTS is orders of magnitude faster than conventional non-differentiable neural architecture search methods. However, it does have a few challenges. It has failure modes. The discovered architectures may have too many skip connections, meaning there are very few learnable parameters in the model. It's also been shown that DARTS might even pick operations which simply inject noise if such operations were present in the search space. So why are there so many skip connections? Previous works have shown that the main culprit is the supernet overfitting the train set, which means that if we can avoid overfitting, we can avoid the failure mode. Now, before we discuss the proposed method, let's briefly review LoRa, which is an important component of our method. LoRa, or LoRa Adaptation, was introduced to improve fine-tuning of large language models. First, it freezes the pre-trained model weights. Then it injects trainable rank decomposition matrices into each layer of the transformer architecture. They have fewer trainable parameters and require less GPU memory. These LoRa modules can be applied to convolutions and not just linear layers. With that, let's now discuss LoRA-DARTS. As the name suggests, LoRA-DARTS combines LoRa and DARTS. We begin by applying LoRa modules to the candidate operations. We then freeze the architectural parameters and train the supernet for a few epochs. After that, we activate the LoRa modules and unfreeze the architectural parameters and train the supernet for the remaining number of epochs. That's basically the method. Let's now look at the results. In the DARTS search space, we ran our experiments on the default implementation of the search space, which we call the weight shared space, as well as weight entangled implementation of the space. In both cases, we observe that there are fewer skip connections compared to DARTS. After every epoch of training, we discretize the supernet to get the dominant architecture at that epoch. We then count the number of skip connections in it and also query the NASBench 301 surrogate benchmark to get the predicted accuracy of the obtained architecture. As you can see in the figure on the right, LoRA-DARTS, shown in green, results in architectures with much fewer skip connections than DARTS. On the left, we see that it has better or similar performance, predicted performance, compared to DARTS. You can see the paper for more results. And with that, we come to the conclusion. We show that LoRa modules in the candidate operations can prevent overfitting. This effectively mitigates the skip connection failure mode. As for computational requirements, the memory overhead associated with the method is negligible, but LoRA-DARTS can take up to 35% longer to complete compared to DARTS. And with that, I conclude my presentation. Thank you very much for your time and attention, and I'll see you at the AUTOML conference.